Okay. Good evening. Stumbling here. This video is a continuation of the previous video that I just made, where I was trying to talk about the reaction of sodium thiosulfate and dilute hydrochloric acid. So, how is it done? We need to understand that rate of chemical reaction can actually be studied by considering how quick the reactants are used up or how quick the products are being formed. In as much as those two things are happening, you'll find that you expect the mass change, the volume change, as well as the change in color. Sometimes the change in color is common in soluble salts. During titration, we actually add the indicator so that the color change is actually exhibited. So these are some of the things that we expect to see during the chemical reaction. And then in all that, these three things are likely to happen. It's either there's going to be a loss in mass, the increase in volume of the gas produced, or maybe the color change during the chemical reaction. And today, this experiment is actually centered just on that. So the things that you need as a material, you actually need materials. You actually need one. You need distilled water. You need sodium thiosulfate. You actually need dilute hydrochloric acid. You need a white paper, a plain paper, where you're gonna draw a cross. 4, you need a conical flask. You need 5. You need at least 2 beakers, measuring cylinders. That's number 6. Measuring cylinders. Yeah. These are the things that you need. But why do you need them? It's for this process. So how is it done? You actually need um, the measuring cylinder to enable you measure sodium thiosulfate. So I'm gonna do a little bit of a demonstration from the procedure that we actually have. So the procedure tells us that we need to, the methodology, we need to measure 50 cubic centimeter of sodium thiosulfate, whose concentration is actually 0.1. So you use a measuring cylinder, we all know how to measure. But above all, we need to understand that when we are measuring, this measuring cylinder has to be placed on an horizontal surface. So we actually measure 50. Qualitatively and quantitatively, we transfer into the conical flask. Okay, we transfer 50 mils. At this point, we have just used the measuring cylinder. We've actually measured sodium thiosulfate, and we've poured in a conical flask. These are the only 3 things that we've used. Of course, you need a stopwatch. I just forgot to include that. You actually need the 7th one, which is the stopwatch to measure the time. Then after that, you use another measuring cylinder now to measure sodium. I will measure hydrochloric acid. How much of it? This time around, we just saw this was 50. But for HCl, we're gonna use the small one to measure just 5 cubic centimeter. So when we do this, we need to prepare a plain paper. That plain paper is put somewhere. That plain paper should have a cross. So we have done this part. We have measured that. We are now drawing a cross, a visible one underneath on the plain paper. Then you actually put the flask on top, the conical flask. Once that is done, we introduce HCl. The moment HCl lands, drops, just few drops, touches the surface of sodium thiosulfate, what do? You start the stopwatch. Start there and then. Now, what is actually happening here is that sodium thiosulfate is reacting with HCl. Sodium thiosulfate is reacting with HCl. And what is actually being formed are a series of products. Okay. What is being formed here are a series of products reacting with HCl. We're going to form sodium chloride. The balancing, you can actually do that. Sodium chloride plus sulfur dioxide plus water plus sulfur solid. So these are a series of products that we're actually forming. So this gas is going to escape out of the beaker, but in a slow manner that we might not even witness. And then, but part of it might dissolve depending on the solubility of sodium sulfur dioxide. You can read about it. And then this is a soluble salt. That's a soluble salt that sits inside of the water. But the presence of the sulfur solid makes this solution in here to become cloudy. So as that cloud solution is turning into being, the cross here starts disappearing slowly, and slowly starts disappearing. Now, the moment you can, that's where they say, so you have to position your eye right from the top here. That's where your eye is, so that you are able to see this cross through the solution. Now, this point says here, as soon as you add the HCl, you start the stopwatch, you look from the above. The moment the cross can no longer be seen, you stop the stopwatch so that we record the time. Remember, the concentration of sodium thiosulfate is 0.1. So you stop the stopwatch so that you record on the time. That's what we have done. Meaning, if we are to go to the table, you can clearly be guided that at this point, at the beginning of a chemical reaction, we only added 50 mils of sodium thiosulfate of that concentration, and the volume was as 50. No water was added. That's why here, the beaker is left out and the water is left out. At point number 2, we're actually going to add the water because we are trying to dilute sodium thiosulfate. So once we dilute it, and then we see what actually happens. So you find that the time it's going to take here, when the concentration of sodium thiosulfate is high, the time is less. Because less time taken, the faster actually the chemical reaction. So we are done with the first part. We got the second part. The moment this thing is done, please discard the solution. Discard everything. We are starting the process. Now, point number 2, we need to dilute sodium thiosulfate. So in our conical flask, we're gonna have, this time around we're measuring 40. So this 40 is actually the first volume. This 40 is our V1. So V1 here is actually 40. Now remember what happens during dilution. The volume increases, the number of moles remains the same, the concentration reduces. So at the end of the day, we expect the concentration of the solution we're going to have to be less than 0.1. But we'll get to that. So after that, how much of water we added? 40. How much of water we adding? We are going to add 10 to a 40. So when you add a 10 to a 40, what final volume are you going to get? Our V2 now gets to be 50. What about the initial concentration? What was it? The initial concentration was 0.1. So at this point, we have even added the water. So why do we need the beaker? Because the beaker is what actually contained water. But in most cases, we use a water bottle to store the water. Okay, so you can have a water bottle, you can have a beaker, but the water bottle is better. So after we've done the dilution, what's gonna be our second concentration? So we're gonna use dilution law. What does this tell us? Dilution law tells us C1, concentration 1, multiplied by V1, the initial volume. The answer you'll get is the same as multiplying the second concentration multiplied by the second volume. This is what dilution law tells us. Now the question is, are we actually gonna convert them? Because these values are in mils, cubic centimeter, you can clearly see here. The question is, are we gonna convert them to cubic decimeter? The answer is yes, the answer is no. Why am I saying yes or no? If you want, you can convert to cubic decimeter, respecting the SI units. But even somebody who is not converted them, the answer is going to be the same. So we're trying to save on time. Even if you do not add, you do not do the conversion, you are pretty good. So we're finding the second concentration. We're going to divide by the second volume throughout. Second volume. So that these guys cancel, and our C2, it's going to be C1 V1 divided by V2. Now, I want you to pay attention to this. The first experiment here, we extracted this from sodium thiosulfate, whose concentration is 0.1. So regardless of the volume that you get from there, the initial concentration of sodium thiosulfate still remains the same. So this is actually not changing. The volume of sodium thiosulfate, not changing. What else is not changing? Across here, the total volume of sodium thiosulfate was 50. Here it was 40 plus 10, 50, 30 plus 20, 50, 20. So across, the final volume is also not changing. So there are only two things that are changing. The initial volume extracted for sodium thiosulfate. After adding water, the final volume, the final concentration also changes. Meaning, this is a formula we're going to use across. This is a formula we're going to use across. Now, in as much as we are using this formula across, we need to bear in mind that the initial concentration is the same, and the final volume is the same. So finding concentration at a particular time, you are just substituting the value of the volume of sodium thiosulfate that you got. Let me say it again. The dilution formula is C1, V1, C2, V2. So across, we are finding the second concentration. So finding concentration, our C1 is the same because we're extracting from the same solution. It's 0.1. It's not changing. So it's V2. The V1 is changing throughout. Initially it was 50. Now we're at 40. The next one will be 30, 20, all the way up to 10. So, and across, when we get a small amount of sodium thiosulfate, a big amount of sodium thiosulfate, we are adding water, and all across the final volume is actually 50, meaning the final volume is not changing. Therefore, this formula will be used throughout, and the only substitution we will be making is for the V1, the volume of the aliquot that we are getting from the beaker. So this is the formula that we'll be using to substitute those values. And therefore, so this is the first reaction, the second reaction, the third reaction, the fourth reaction, and the fifth reaction. Now we're trying to talk about the concentration of sodium thiosulfate for the second reaction. So we're gonna say C2 is gonna be, so C1, allow me to write it here. It's not changing, 0.1 over the final volume is 50. I'm not converting because the conversion factor for the denominator and the numerator is the same. So the only thing that will be substituting, like I said, is a volume. So when you substitute the volume here, you actually put it here, 40. When you do the computation, the volume is gonna be 0.5. So the same thing, you add 40 mils of water, you 40 mils of sodium thiosulfate, you add 10 mils of water, you dilute it, then you add an HCl. Upon adding HCl, you start a stopwatch. After the cross disappears, you stop the stopwatch, you record the time here. And the concentration, when you do this, it's gonna be 0.08. That is a value you find here. After you're done, you discard. You go to experiment number 3. Experiment number 3, the amount of sodium thiosulfate we are getting here is 30. Therefore, our V1 now changes to 30. Our final volume still 50 because we're adding 20 to that 30, which gives us 50. And when you plug in them in there, you multiply, the concentration reduces to 0.6, and that is the 0.6 that we have here. You do the same. Experiment number 4, we are now adding 20. So meaning here, we are now gonna put a 20, we're gonna put a 20 here, and the final volume is the same. You don't have to change anything. So we're actually putting a 20 here. And when you multiply, you're gonna have 0.4. The same thing, you put 10, you're gonna have 0.2. So these are different concentrations across during the reaction. Now, what conclusion can you get from here, even before we go to answering follow-up questions? When the concentration of the reactant is very high, we expect the reaction to be fast, and fast reactions take less time. That's what we expect. So we expect the time here to be increasing, of course, increasing while the concentration is decreasing. So what type of stuff can you get from here? Mathematically, we can see that the concentration of sodium thiosulfate and the time recorded are inversely proportional to each other. Because when we reduce the concentration, time is increasing. As a result, if this is to be plotted, you expect to have a graph of that nature with a negative gradient because it is an inverse proportion. Now, what do we have? So you need to remember that. Now, what do we have? So we have all that done. The next thing that the question tells us is to do the data analysis. So we go to analyze the data that we have. Time, I've not indicated time because you actually collect the time during the experiment. So I was just showing how to find the concentration. Now, how do you fill up in the blank spaces? You record the time. You also do the calculations I've already indicated for the concentration there. It's the plotting. It's the plotting. Now, I can agree with you, or I can tell you something that the concentration or the duration here, the time may even be 600 because the concentration of sodium thiosulfate is very low. So the startup reaction, we expect to be very slow. But as we dilute it from 0.1 to 0.02, we expect time to go as far as 1,000 of seconds. So you can actually, no, not 600, maybe 200, maybe even 120. Yeah, because we're likely to get maybe 2 minutes or something. So we are plotting this on the graph. And graphically, we might obtain something like this. Just an example. So alongside here on the x-axis, we understand that we've got time, which is increasing. Then here on this side, we expect to have concentration of sodium thiosulfate, and we'd expect to have a negative graph, or a graph of that way with a negative gradient. So the plotting, I know you have been taught how to come up with a scale, basing actually on the figures that you have and stuff like that. So you plot using the time and the graph. Hints. The question here says 4 marks. How do you get these 4 marks? Please put a title. You omit the title, you lose marks. What is a title? Where do you get the title? It's in the question. The question says plot. So the question starts from here. The title starts from here. The graph of concentration of sodium thiosulfate against time. It's very important so that you tell us that what is on the y-axis is the concentration of sodium thiosulfate and what's on the x-axis is time. So please put a title on your graph, title first. Once that is done, you need, now the title tells us that this is all the concentration, so you indicate concentration in moles per liter, and this is time, it's converted to seconds. Now you'll find that when you are doing this experiment, because of the slowness of the reaction, it might actually go to minutes. Please convert them to seconds. So here you're likely to get a mark. You're actually likely to get a mark on the title. You're likely to get a mark here. Now, when I put a mark here, I mean labeling the axis as well as using the appropriate scale. Here you have a mark labeling the axis, the y-axis, as well as putting the appropriate scale. The title also, you write, plus how neat your graph is, you're likely to have 4 marks. So without a title, make sure that you start expecting 3 marks. Labeling the axis not indicated, make sure you expect low marks. Worse still, if you don't even use the appropriate scale, you expect to lose marks. But this one again says, determine the rate of a chemical reaction when 20 mL of water was added. I'm going to use this graph. It's different. I cannot use the actual graph for the question because some of the students might have not done this question. So how do you do it? Go back to your graph. When 20 mL of water was added, it's on at this point where 20 mL of water was added, and the concentration was 0.06. So go on your graph, and look for the concentration, which is 0.06. So 0.06 actually, let me put a title here, 0.06, I'm just giving an example, could have been maybe somewhere here. I'm just giving an example. Okay, let me change, because if this is 0.1, 0.08, 0.06. So if this is where, I'm just giving an example, you use your graph. So if this is where the 0.06 is, you do know that the point is somewhere there. What are you supposed to do? We are trying to do an instantaneous rate of a chemical reaction. Please plot a tangent. You need to draw a tangent passing through that point. Please draw a tangent passing through that point, and then within this tangent, find 2 points. that will help you to find the gradient. That will help you to find the gradient. At that point, when the concentration is 0.6, you know where the point is on the graph. Please draw the tangent. So this actually that you have drawn is called the tangent. So at the point on the tangent, find the gradient. How do you find the gradient? So first of all, you draw the tangent, then find the gradient. How do you find the gradient? So gradient in mathematics, gradient is given by the change delta y. Remember the dy dx in mathematics, the calculus? So the delta y, the change in y over the change in x. There are no shortcuts. What are the change in y? We're talking about the change in value between, remember, that point represents the y-axis somewhere there, and that point represents the y-axis. These are the points that I have chosen. You can choose points of your own. You can even use one of the points that you already have, then you just pick one point. So it depends on the points that you've picked. So if you've picked this, let this be maybe your y2, and this point here be your y1. This is a change in y from y2 to y1. So when I say change in y, this is what I mean. So you do y2 minus y. This we have done, guys, in coordinate geometry. y2 over y1. Even if you switch, my y2 being your y1 is still the same. What about the change in x? The same thing. So this point here, if you drop it on the y-axis, on the x-axis, now if this is your y1, this can be your x1. And somewhere here, if that was your y2, then this becomes your x2. So that you say x2 minus x1. You plug in the value and you'll find that you're gonna have a negative value. The same answer you have, just please take the modulus function. What I mean is just make it positive because you cannot have the rate which is negative. So the same answer you find, just make it positive. And what will be the units? The change in y, what do you have on top? We have moles per liter per second. So in short, you can just say moles second per liter. So you know what to do. Or if you feel that concentration moles per liter is not helping you find the right answer, remember that concentration can also be found in molarity. So just say molarity per second. So the value that you're gonna find as a negative, turn it into a positive, then supply the answer with these units as molarity per second. That's all you need. So here I need a formula here. I also need the final answer with the right units, gets you to marks. And make sure that all your computations are in pen. Anything in pencil is never marked during exam other than the graph. So now how do you explain the effect of concentration on a chemical reaction? You know what's happening. The reason as to why we have obtained a negative gradient, it's because the reducing in concentration was also reducing the rate of a chemical reaction. That's why it was taking a lot of time. So you can say the reduction in concentration of what? Of reactants. Reactants reduces the rate of a chemical reaction. Or you say the higher the concentration, the faster the rate of a chemical reaction. So there are many ways in which we can actually explain this question. So you need to be smart. Data collection, you can use a pencil to collect the data, but when you are writing the report to submit, you make sure that all your writings are in pen, except for the plotting. But even these numbers here, you should be very smart. Even these numbers here, you make sure that you write them in pen. The title, the labeling of the axis, and all those things. So that's how you actually analyze this question. In case there are any clarities, in case there are any uncertainties, please do not hesitate to drop me a text. I'll be able to actually find it. Yeah, so you can send me an email or you can drop a text on 26 0975578 694. You can drop me an email on kunde59 at gmail.com. I wouldn't send an work email. That is enough. Okay. So I think that's all you guys can do. I want you guys to take enough time to go through this work, and then you see how best you can do. Remember, SBAs are very important because they actually help you to better your results. Help you to better your results. So make sure you do it diligently, pay attention to details, and do the right thing at each time. Thank you so much.